Welcome all of you to the chemistry online classes. In our last class, we have discussed about the 3 examples of the VBT, and today this is the last example for the VBT which is mentioned in your NCERT book. Let us go for that one. Here NiCN 4 times minus 2 is the given complex ion. So, for this we need to find out the hybridization and its geometry and its magnetic properties. So, let us go for the central metal atom. Which is the central metal atom here? Nickel is the central metal atom whose atomic number is 28. So, the configuration will be 1s2, 2s2, 2p6, 3p6. Okay. So, this is the electronic configuration of the nickel. So, now I need to find out the oxidation state of the nickel. So, just go for it, x plus 4 into minus 1, which is equivalent to minus 2. So, x will be having the value of plus 2. It means Ni is present in plus 2 form. So, Ni plus 2 configuration will be remove the 2 electrons from the outer cell. (4s) 0. Okay. So, now Ni plus 2, this is the here 3D, this is 4s and this is 4p. 8 electrons I have to fill. First occupy the electrons singly, 4, 5, 6, 7, 8. Okay. So, now the CN wants to get or to make the complex with the nickel. So, the CN is the strong ligand. CN is the strong ligand. It makes this electron to get paired here. So, the pairing will going to be occurs. Here it is 4s0, 4p0, here it is 3d8 and here 4s, this is 4p. Okay. So, now here how many CN are there? 4 CN are there. It means 4 orbitals are required. Which are those 4 orbitals? This is one of the D, one of the S and 2 of the P. It means these 3 orbitals undergo hybridization and they will going to produce dsp2 hybridization. These undergoes dsp2 hybridization and they will form dsp2 hybrid orbitals like this. This is 3d orbital, while these are the 4, one of the D, one of the S, 2 of the P and 1 P will be empty. Okay, these are the dsp2 hybrid orbitals. Okay, and these dsp2 hybrid orbitals are occupied by the electron pairs donated by the ligand, and the ligand donates the electron and it makes the coordinate bond with the central metal atom nickel. It donates its electron and forms the coordinate bond in order to form the complex. So, each CN can donate one pair of the electron. So, these hybrid orbitals are occupied by the 4 lone pair of the electron. These are the 4, it means 8 electrons, or these 4 pair of electron is donated by ligand CN. Okay. And now we will discuss about hybridization. Which type of the hybridization will going to be takes place here? That is dsp2 hybridization takes place. And what about geometry? Geometry is square planar. Geometry is square planar. Okay. And then what about magnetic property? magnetic property. So, is there any lone pair of electron? No. So, it is diamagnetic. So, if I draw the structure, how it will be? Ni in the form of +2 and then square planar. 4 CNs are donating its lone pair of electron towards the central metal atom in order to form the coordinate bond. So, there is a formation of the square planar complex like this, and the charge on this one is, that is -2 donated by Cn. So, this is how we can explain about this one more complex. See here, first just look at the complex, then find out the central metal atom. So, which is the central metal atom? Nickel. So, what is its atomic number? Its atomic number is 28 and its electronic configuration is written in this format. Now, find out the oxidation state of the central metal atom. It is in the form of +2. So, you have to remove the 2 electrons from the outer shell. So, I have removed 4s electrons. So, what will be the configuration? It will be of the form of 3d8. So, now just you look at the ligand, whether the ligand is strong or weak. Whether the ligand is strong or weak. For your syllabus, I have solved the 4 complex. In that 4 complex, NH3 and Cn are the strong ligand. NH3 and Cn are the strong ligand, okay, while Cl minus, F minus, these are the weak ligands. So, the strong ligand make the electrons to get paired up. So, our Cn is also a strong ligand, that is Cn minus is a strong ligand. So, it makes these electrons to get paired up. This makes these electrons to get paired up, and just you look at the other orbitals and just you think of the ligand. How many ligands are there? 4 are there. Each can donate 1 pair of the electron. So, it needs 4 orbitals, that is 4 hybrid orbitals. These one of the d, one of the s, 2 of the p orbital undergo hybridization to produce identical hybrid orbitals. So, here we got the dsp2 hybrid orbitals. And these dsp2 hybrid orbitals are filled by the lone pair of the electron donated by the ligand in order to form the coordinate bond. So, here the 4 pair of the electron are donated by the ligand Cn minus. Clear? So, when the Cn will going to donate its lone pair towards the nickel, so there is a formation of the complex will going to be takes place. And what about its hybridization? Hybridization is of about dsp2 and the geometry is a square planar. It's if we represent the geometry, it will be like this, square planar, and magnetic property, it is a diamagnetic because there is no unpaired electron. So, these are the 4 examples which you need to know. And these 4 examples are very important because any one of the example will be asked in your examination on the basis of the VBT. Explain the hybridization, geometry and magnetic property of the following complex ion. Like that they are going to give you the question for 3 marks. So, be aware of that. Just in all the 4 cases, first look at the central metal atom and remember its atomic number and write down the configuration later. So, find out the oxidation state. According to the oxidation state, remove the outer electrons. Okay, then arrange it. After arranging, you just look at the ligand, whether the ligand is strong or weak. If it is strong, you can go for the pairing of electron. Then it will be a diamagnetic, probably it will be a diamagnetic. Then if it is a weak ligand, it does not allow to pair up. They will take the outer orbitals like that. Okay, it does not allow to get pair up. So, during that time what happens? Again ligand will going to be weak, means no pairing. So, further procedure will going to be carry on. Okay. So, this is how we can explain the one more example. Clear? So, now whatever I have explained the 4 examples, those are on basis of the VBT, that is valence bond theory. Now, this is the bit of the topic where we are going to discuss about the limitations of the VBT. So, what are the limitations? Okay, or demerits you can consider the demerits of the VBT. The VBT does not explain the color of the It does not explain about the color exhibited by the coordination compounds or coordination complexes. The coordination compounds will going to exhibit the color, the complex will going to be exhibit color. Regarding that, the VBT does not explain anything. Okay, so this is the drawback. The first drawback is it does not explain about the color exhibited by the coordination compounds. So it means whenever the complex is formed, they will going to exhibit the color. Why that color is observed, that is not explained by the VBT, that is the drawback of the VBT. The second point, it does not distinguish between the strong and weak ligand. It never said which is strong VBT. According to VBT, we cannot able to predict which is strong or which is weak. That is also the drawback. That's why it does not distinguish between the strong and weak ligand. And the third one, it does not give exact prediction about the tetrahedral and square planar structure of the coordination complex. See here, whenever the ligands are 4 like this, ML4 like this, yeah, it means, or any complex you can take like this. This is the central metal atom, these are the 4 ligands. If there are 4 ligands, it can even get the that what we can say, we can predict its geometry as a tetrahedral or square planar. Previously, one more example I have solved, there is no square planar, there is a tetrahedral, that is I think NiCl4. That example NiCl4, we have the 4 ligands are there, but the shape will be tetrahedral. The shape depends upon, or the geometry depends upon the further hybridization. Which type of the hybridization depends upon that we can predict the geometry. So here, but VBT does not give the exact prediction about tetrahedral and square planar structure of the coordination compounds. And then it involves number of assumptions. It means many ideas they have given, that is also not a merit, it is also a demerit of this VBT. It involves a number of the assumptions, and then does not give the quantitative prediction of magnetic data. Clearly does not explain about the magnetic data of the complexes. That is also the drawback of the VBT. And the last point, does not explain the kinetic stability of the coordination compounds. So all these are the limitations of the VBT. Just you need to know, not that much important, but you need to know why VBT is also not having the, why it is also having the demerits, because it cannot explain few of the points which I have written here. So these are we can consider as a limitations of the VBT. Clear? So let us go for the one more important bit of the topic, that is magnetic properties. So the magnetic properties, so as you know, the magnetic properties is that is the magnetic moment. The magnetic, it means the magnetic properties are exhibited by the coordination compounds. That is, magnetic moment is represented by mu, and its formula is square root of n into n plus 2. So here mu is the magnetic moment, and here n is the number of unpaired electron, number of the unpaired electron. So how to calculate? On the basis of this formula, we can predict whether what we can say, the given complex is paramagnetic or diamagnetic. One more thing, if it is attracted by the magnetic field, if there is a attraction with the magnetic field, means that is a paramagnetic. So when the paramagnetic behavior is possible, when there is a presence of the lone pair of electron. Okay, and there is a repulsion. That means that is a diamagnetic. Okay, diamagnetic properties present when there is a absence of lone pair of electron. Okay. So, here the magnetic properties, it means whether the given complex is paramagnetic or diamagnetic. How it is calculated on the basis of the formula, that is mu is equal to square root of n into n plus 2, and Bohr magneton, its unit is Bohr magneton, that is Bm we are going to write, where mu is the magnetic moment and n is nothing but a number of the unpaired electrons. Okay. For example, if I need to find out the magnetic moment of the Ni plus 2, okay. Here also the same thing, Ni is in the form of plus 2. So, what will be the configuration? Only at the end I will write like this 3d8 4s0. I hope you are getting exactly what I am writing. Ni in the plus 2 form. How many electrons are there in the D? First you draw the 5 orbitals here and arrange the electrons 1, 2, 3, 4, 5, then it is 6, it is 7, it is 8. So, now you calculate how many electrons are there, how many unpaired electrons are there, 2 unpaired electrons are there. So, the Ni plus 2 magnetic moment, that is mu is equal to square root of n into n plus 2 is there, where n value is here, n is nothing but number of unpaired electrons. How many unpaired electrons are there? 2 electrons are there. Okay, 2 square bracket, and if you simplify this, it will be around 2.82 Bohr magnet. Like this, we are going to find out the magnetic property on the basis of this formula, that is magnetic moment is calculated by the mu is equal to square root of n into n plus 2. I hope so even you learned this in case of the D and F block elements. So, few more example I will tell for the magnetic properties. So, you can able to understand how the ligand has the influence on this. Okay. On the basis of the ligand, here pairing will going to be takes place or pairing is not going to, if pairing occurs means how many unpaired electrons remain. If it is not so, lone pair will be there. If pairing occurs during that time, usually lone pair of the electrons are not available. During that time, it will act as a diamagnetic. So, this is how we are going to explain. I hope so you are getting what exactly I am telling. So, this is the important bit of the topic, that 4 examples on the basis of the VBT. I hope so this is also clear, because Cn is a strong ligand, it makes this part to get pair up and further orbitals undergoes d-sp2 hybridization, and 4 orbitals are available for the 4 Cn. Each Cn can donate 1 pair of the electron here. Like this, it will going to predict a square planar geometry, and it is a diamagnetic because absence of the lone pair of the electron, and its geometry is square planar and its hybridization is d-sp2. And these are the limitations of the VBT, which are not that much important, but you need to remember at least, just you need to know why it is, why it has the demerit like that. Okay. And the last bit here is, in this video last bit is magnetic property, and this is important also, mu is equal to square root of n into n. So, see here we are taking few of the example. Here we need to find out the magnetic property of this complex on the basis of the given formula. So, just look at this complex here. First, you need to find out the oxidation state of the Fe, because I want the electronic configuration, I want to remove the outer electrons. Fe is in which state I need to know. So, the oxidation state of the Fe I need to find out. This is X and 6 Cn, 6 into minus 1, which is equivalent to minus 3. So, the value of the X here is, that is plus 3. So, it indicates what? Fe is in the form of Fe plus 3. Fe is in the form of Fe plus 3. First, write down the configuration of the Fe. You can able to understand what exactly the configuration is there. So, the atomic number of the Fe is 26. So, the configuration will be 1s2, 2s2, 2p6, 3s2, 3p6, and then 3d and 4s. 4s2, for this it is 20 and here d6. Okay. So, it is in the plus 3 form, means we have to remove the 3 electrons, that is 3 electrons from the outer we have to remove. Fe is in the form of Fe plus 3. So, the configuration will be 1s2, 2s2, 2p6, 3s2, 3p6 and then 3d5, 4s0. Am I correct? 3 electrons I have removed, 2 electrons from the 4s orbital and 1 more electron from the 3d. Totally 3 electrons are removed. Now what about d? That is 3d5, like this configuration is there. 1, 2, 3, 4, 5. So directly now you don't go for mu is equal to square root of n into n plus 2 like that. Okay, why? Here Fe is not only Fe plus 3 form, because it is making the complex with the Cn. Cn is the strong ligand which makes these electrons to get paired up. So you have to think about the ligand. If the ligand is strong, I said you several times, if the ligand is strong, it makes these electrons to get paired up. So first make the pairing of this electron. So when the Cn approaches here, during that time what happens? The pairing, see here, one of the electron will go here like this, totally 2, 4, 5 electrons. Okay. So now you think about how many unpaired electrons remain. Only one unpaired electron is remained. Only one unpaired electron is remained. Okay. So here now mu is equals to square root of n into n plus 2. So square root of n is 1 into 1 plus 2. Three d5 is there, d5, and then here pairing will going to be takes place 1, 2, 2, 4, 5, and then one unpaired electron remain. So if the unpaired electrons are 1, that one hint it will be around 1.7 Bohr magneton. So its value is 1.7 Bohr magneton. So now we can say it is whether paramagnetic or diamagnetic. It is paramagnetic because unpaired electrons are present. So it is a paramagnetic complex with the one unpaired electron. So let us go for one more example. Here Fe, F6 is there. In both the cases the central metal atom is iron only. But the thing is the ligands are different. Here it is a strong field ligand, here it is a weak field ligand. So now here the ligand is weak field ligand, although we can go here. Okay. So now here find out the oxidation state, X plus 6 into minus 1 which is equivalent to minus 3. Therefore, X is equals to plus 3. Same, here also X is equal to plus 3, here also X is equal to plus 3, because in both the cases 6 ligands are there. Here 6 Cn are there, here 6 F are there. So no need to worry about it. Directly I will go like this. So what is the 3d5 and 4s0 is there. So like this, Fe plus 3 means 3d5 and 4s0. Now 3d. So how many unpaired electrons are there? 5. Okay, I have arranged like this. But the F, that is fluorido ligand, is a weak field ligand. It does not force these pair of the electron to get paired. So these, it is not forcing means how many unpaired electrons are remained here? 5 unpaired electrons are remained here. So the value of mu is equal to square root of n into n plus 2. So n, what is the n? N is nothing but number of the unpaired electron. So square root of 5 into 5 plus 2. So if you calculate this, it will be around 5.91 Bohr magneton. So this is also the paramagnetic. This is also the paramagnetic. Both the complexes are paramagnetic in nature, but this is paramagnetic with the 5 unpaired electron because it consisting of the weak field ligand, while here it is also a paramagnetic complex with the 1 unpaired electron, and here it consisting of the strong field ligand. I hope so it is clear for you. You go on simplifying here. So if it consisting of the unpaired electrons, you are going to, it consisting of the unpaired electrons means it will act as a paramagnetic or else it acts as a diamagnetic. Okay, let us go for the few more examples here. This is also para, this is also para. So let us go for this one. Here, central metal atom is Mn. First, I need to know the configuration. I need to know the oxidation number. Plus 6 into minus 1, which is equivalent to minus 3, is it indicates X is equals to plus 3. Manganese, Mn, its atomic number is 25. So 1s2, 2s2, 2p6, 3s2, 3p6, and then 3d4s. Okay, 4s2, 3d5. 25 means 3d5, 4s2. So now it is in the plus 3 form. So how many electrons I have removed? I have to remove the 3 electrons from the outer cell, 2 electrons from the 4s and 1 electron from the 3d. So what will be the Mn plus 3? Only last orbital I will write here, 3d. Only 1 electron will be removed, 3d4. Okay, it will be a 3d4 format. Now draw the d orbital. D orbital. Okay, and here what happens? 1, 2, 3, 4. Cn is a strong ligand. Cn is a strong ligand. So what it makes? It will going to make the pairing of the electron will going to be takes place. So the pairing will going to be only 1 electron will going to be get paired here. Only 1 electron will going to be paired here. Why only 1 electron will going to be get paired here? Because in case of the, if you observe, we have the configuration of D2 sp3 or sp3 D2, but we do not have the D3. D3 is not possible. D3 is not possible, as D3 is not possible here. So only 1 electron will going to be pair up. So what, how it will going to be takes place? 1 electron it will going to pair up, another 2 unpaired electrons is remained. So why this is D2 and D3 here? Suppose, I will tell you the possibility. Suppose 5. Okay, these all pairing will going to be takes place, 1, 2, like this, 4 electrons. So how many D are available for the hybridization? 3, D3, but D3, that what we can say hybridization is not possible. So only 1 electron pair up like this. Only 1 electron will going to be pair up, another 2 will remain as it is. So now how many orbitals are available? D2 are available for the hybridization. So only 1 electron will going to be pair up here. How many unpaired electrons are remain? 2 unpaired. Now you can calculate mu is equal to square root of n into n plus 2. N is square root of 2, 2 into 2 plus 2. Approximately it is around 2.82 Bohr magneton. Mu value is 2.82 Bohr magneton. So it is a paramagnetic. Clear? So next here, first oxidation state, x plus 6 into minus 1, which is equals to minus 3, x is equals to plus 3. Again the same thing, Mn is in the form of the plus 3 only. I said you, in both the cases 6 ligands are there, but here it is strong, there it is a weak. So if it is weak or strong, that is also matters. So Mn in the form of plus 3 means directly I will go for 3d4 and 4s0. Now how it will be a d4, 1, 2, 3, 4 electrons are there. So, one more orbital is empty. Clear? So, what about Cl? Cl is a weak ligand. Cl is a weak ligand. It does not make to get paired. It does not want it. These electron will not going to be pair up because it is a weak field ligand. So, the unpaired electrons are 4 itself. N is n into square root of n into n plus 2. So, how many unpaired electrons? 4 into 4 plus 2, it will be around 4.89 Bohr magneton. So, it is also a paramagnetic. I hope so it is clear for you. First, look at the central metal atom in all the cases and then find out its oxidation state, because you need to know which form it is. It is in the +2 form or +3 form, you need to know. Then remove that many those many electrons from the outer orbit. After removing, arrange the electrons like this. After arranging, just think about the ligand. If the ligand is strong, make pairing. Okay, if it is weak, don't go for the pairing. Here it is strong, it makes pairing, and one electron is remained and it is act as a paramagnetic. And here also the same thing. And here I will give you 2 examples as a homework. If you understood this concept, you can able to say whether those complexes are diamagnetic or paramagnetic or whatever. So, the first example is cobalt -2, and one more example is cobalt F6 -3. So, these 2 you can take as a homework and you can solve like this. So, predict whether it is a diamagnetic or paramagnetic. Okay. So, the magnetic properties are, that is calculated with the help of this formula, mu is equal to square root of n into n plus 2, where mu is the magnetic moment, n is the number of unpaired electrons. So, in the given complex, first find out the oxidation state, then write down the configuration. According to the oxidation state, remove the outer electrons, then arrange those electrons in the 3D orbital. So, then think of the ligand is strong or weak. If it is strong, definitely go for pairing, and one of the here it is a different case. Do not go for pairing all, you should take only one here. Okay, it is somewhat different example, and go for the pairing if it is a strong. Then find out the number of unpaired electrons and then you can find out the value of mu. So, you can predict it as a paramagnetic. If there is no unpaired electron, its mu value will be 0 and it acts as a diamagnetic. And then if it is a weak ligand, do not go for pairing, you will get a many number of the unpaired electrons. So, you can calculate its mu value. And these are the 2 homeworks which I am giving you. If you understood the concept, then you can able to solve these 2. If you are not getting, you can contact me. If you are not getting anything, just look at the video one more time, so you will get the clarity. So, for this we will end this class, and till now we have discussed about the VBT and its drawbacks, and on the basis of the VBT we have even explained about the magnetic properties. In our next class we are going to discuss about the crystal field theory. That is the last bit of the topic, and that we are going to start in our next class. Until that, keep watching the video and write down the whatever the points I am written on the board, and solve these 2 homework on the basis of the concept which I have explained. Okay, thank you.